Okay, and a good morning to everyone. And that was Fleetwood Mac, Don't Stop Thinking About Tomorrow. And a reminder to you, less than 2 weeks from now, we have our first exam. And that's going to cover chapters 1 through 5. We've done 1 through 3 already. We start today, depending on how your questions are, on Chapter 3, homework, but we'll be talking about bivariate data analysis. We'll be doing correlation and regression. So just a reminder that you need to spend some time reviewing slope-intercept form of graphing of a linear equation in 2 variables. So that means you should be able to draw a coordinate axis system, plot a few points, draw a straight line, and in a reverse way, if I give you 2 points, determine the equation of that line. I would expect you to be able to plot, say, 20 points on a coordinate system in less than 10 minutes, more like 5 minutes. And so you need to review some of that because it seems, at least from the past, that as a process is something that takes much more time than it should. So that's where we're headed this week. I'd like to go to the document cam for a moment. And as we go to there, we've looked at this link, this flash page, and the particular Math 134 where you link to the home page. But I'd like you to note the equation that's there. Can you tell me what that represents? We've talked about it before. What does little sigma represent? It's a standard deviation for a sample or a population. Okay, coming off there for a moment. Greek letters for population. So that should be a population standard deviation. Now, look at the left side of the equation as we bring that up again. That's sigma sub x bar. Okay, so that is the standard deviation of the sampling distribution of the sample means we did in the first week. Now we had as our title song, Don't Stop Thinking About Tomorrow, but going in reverse, don't stop thinking about yesterday. The first week we took 18 means. We looked at the standard deviation of those 18 means. Okay, and the argument is that that's supposed to be approximately the standard deviation of your population divided by the square root of your sample size. So if we go to the board for a moment, just look at that as an idea. We're saying that sigma sub x bar is going to be the standard deviation of your population divided by the square root of the sample size. So in the problem we did in the first week, we had a sample size of 10, correct? So we would divide by the square root of 10. And then the population standard deviation of birth rates. If we were to bring that up and stack graphics at this point, and you saw that as part of your output for the lab 3. The default was to give you the standard deviation. So I'd like to tie together a little bit of what you were seeing in lab 3 with what you see in this page that you reference to get to information about the course. So I need to bring up stack graphics for just a moment, and as I do that, let me take a moment to first minimize what we were just looking at, bring up the web page here that I need. Okay, as we come to this page on the computer, just a reminder that we go to the third icon, we open up the data file, and without showing you where the pop-up came, we saw this, we went to describe, we went to numeric data, we went to one variable analysis, we went to birth, and you did an OK, and this is the analysis you had. And down here, at the bottom of that page, you had some information. In particular, you had a standard deviation. This is just the default of what came up. Now, I ask you to deselect certain things, but you had the count. We wanted the minimum, the maximum to get your histogram. But note, there is a standard deviation, which to the nearest tenth would just be 11. So if I put this up here as an 11 for a moment, then the square root of 10 is roughly pi. It's roughly 3. So if I look at that, then I would have 11 over 3, which is roughly
4.
Well, okay, you could say roughly 4, 3 and 2/3. So this is roughly 11 over 3, just rounding off, and that's 3 and 2/3 for the standard deviation of the sample means. Now that means the entire set that's possible. And I think we said that was about 60 quadrillion. We had 18. But that is what this symbol that you look at each time we go to the web page represents. So if I bring back up the web page and scroll down just a little bit, there is your sigma sub x bar. We have a name for that. We call it the standard error of the mean. So as I come back to the board, we're going to call this the standard error of the mean. And this is just something that comes out of week 1 and our web page. Now, the intent of going back to the computer as we look at it is to click on this page and just remind you that we get, of course, the web page for the course. And as we scroll down there, we have the schedule. So let me bring that in and move over just a little bit. And by the way, note, at the bottom of the screen, there is an EL531 bivariate data video. And you're going to be entering bivariate data, meaning X and Y, into your calculator. And that is a link that will help you as you do that. I'll be doing some of that as we go through the presentation. But here is the on-campus schedule. So I'm going to click there. And then as I scroll down, just a reminder that we are in, let's see, got carried away there. There we go, September 15th. We are in week 4, and we are going to be doing chapter 4 and lab 5. Please note, we are not doing lab 4. So if you do lab 4 because you're doing it sequentially, I appreciate the initiative, but you won't get credit. Then in week 5, September 22nd, please note that on the 25th, you have an exam. We cover Chapter 5 and Lab 6 before that exam. The reason I want to bring that up is that typically your labs have been due on Thursdays. Next week, your lab will be due the morning of the exam. And we meet at 6 a.m. for the exam to 8 a.m. You expect to be here at 5:45. If you have conflicts with that for some reason, you need to notify me and we can try to make other arrangements. But the exams are 2 hours long, so they go from 6 a.m. to 8 a.m. And you're expected then to be here about 15 minutes before that, so you get settled. And that's when that lab is due. I want the lab done prior to the exam, so that is something that you'll want to do. In addition to that, I have mentioned to you that there are 60-some short answer questions. Let's go back to the computer. Notice exam 1 is listed there. We've talked about this earlier, but I'll talk about it again. We click on exam 1, and you'll see that there is a list of typical short answer discussion questions. And all you have to do is click on this link, and I'll show you the whole page. That was an FAQ on an exams. So I'm simply clicking on that link, and we get discussion questions exam 1. And this is what we've talked about before, but again, the difference between a statistic and a parameter, that has to do with what we just talked about a moment ago, and I have on the board. So what would be the difference between a statistic and a parameter? You should be able to address that now after 3 weeks. What's the difference in notation? Okay, a statistics for a sample, a parameters for a population. We listened to the alliteration. That's good. What did I just say less than 10 minutes ago about Greek letters? Let's go to the board with what I have up there for a moment, Jennifer. We used a Greek letter. What did it represent? A standard deviation for a population. So let's go back to the document, Cam. So when it says a statistic and a parameter, the notation is different. English letters for the statistic, a Greek letter for the parameter. They are a measure, a numerical measure of either a sample or a population. And in this particular case, it was the standard deviation, which is a measure of spread. So that's pulling together week 1, week 3, and week 5. Odd numbers, 1, 3, and 5. And there are 67, I believe, questions there that I encourage you to go through. Don't wait until Wednesday night to look at them, of the night before the test. Start going through them and see what you can do, and then we will be spending time next week answering questions regarding those short answer questions. So that was the first thing I wanted to point out, and then I'm going to back up on Internet Explorer for the moment and go back to a previous page. Okay, and as I go to the left side of this frame, let's go down there, Homework Assignments 4th edition. And of course, that's what we're talking about this morning, in the sense that we have Chapter 3 problems that we need to focus on. So just to point out, these are the problems that we need to look at this morning, which start with number 2 and end up with 46. And we're going to answer questions regarding those problems. However, as I scroll down, just to remind you, there are problems for both Chapter 4 and Chapter 5. Well, I'm trying to get between there, not doing a very good job, so let me instead go, there we go. Now I can scroll down maybe and get to 4 and 5 simultaneously. And I'll just move this up. There are 20 more problems that must be done before the exam. So Chapter 4 looks like it's just this week. But what you're going to find as I talk about bivariate data analysis, I will be covering 4 and 5 pretty much at the same time. Now, one of them talks about how you go ahead and you, in plotting a set of points, try to draw a line that contains as many of those points as possible. We call that a regression line. And we try to get the equation of that line. Now, that's one chapter. We would like to have an equation of the line so that we can estimate values of y for values of x. So we can predict something. In our case, we might want to try to predict birth rates knowing literacy, female literacy. So you go into a country, you look at how female literacy is, and you try to predict what the birth rate would be. Is the relationship a strong one or a weak one? That'll be a question we address. And that relates to how many points are close to the line that you draw. We call that a relationship between two variables, so it's a co-relationship, so we refer to it as correlation. So in one case, we're going to be looking at the equation of a line, and I'm going to again go to the board for that. So the equation for the line is going to be, at least from the standpoint of today, what you did in algebra. And this unfortunately gets tweaked a little bit because we don't use M and B. But that's what you remember from algebra, I hope, that slope intercept. So we talk about the regression line. We're going to introduce another letter called R for the sample correlation coefficient. So that will be part of a separate chapter, but it's difficult to talk about those two parsed out that way. So I will be covering the content simultaneously starting today going up through next Wednesday. So as you look at the problems in the text, don't think of doing just chapter 4 this week and relegating 5 to the following week, in which time you're going to then try to get ready for the test. You will need to have your calculator in a very serious way this week, because we are going to enter bivariate data and use it for some formulas that are very difficult to do without the calculator. And I handed out to you the first week a set of formulas. You need to find that page. We're going to make extensive reference to it. That page is not in your text. The formulas aren't in your text. Okay? So that's where we're headed in terms of the next 2 weeks. And I want you to just understand that a lot of work is ahead of us, but you can't look at it in a linear fashion and argue that you can wait until next week to even consider Chapter 5. So with that said, let's go to questions on Chapter 3. My intent is to collect Chapter 3 today, assuming that there aren't extensive problems with the chapter. So do you have any questions you want to address in Chapter 3?
Number 42.
42. Any others, just so I have an idea of how extensive it is? Number 42 and?
2.
Number 2?
46.
46.
31.
31. 12. Okay. Let's see what we have going here then as I go off the laptop for a moment, and I'm going to come back shortly. What we're going to do is start with problem 2, which I'm glad to see there was a question on, because this is a problem related to a density curve. And so we need to point out some things about the density curve. This is one I would have liked to have had time to cover before the weekend. We ended up taking longer to talk about density curves than I intended when we started that. We are on page 69, problem number 2. So I'd like to contrast two things here. One is in the general way, and of course that was part of the purpose of Lab 3, was to understand that ideally we would like to have what for our density curve? What is the goal? What would be ideal? A bell shape. That's what I'd like. Do I always get it? And the answer is no. Lab 3 was a case in point. Now may I remind you that when you draw your density curve, the density curve should not touch the x-axis. So I don't want half parabolas. So if you do that, I will be taking points off on homework. So make sure that your density curve does not come down and just hit the axis. It is asymptotic. Okay? It should look like a bell, not like a portion of a circle or a parabola. Now, not all density curves are bell-shaped. I gave you 2 counterpoints in the lab. What were those 2 counterpoints? In the lab. Some of you ignored it, but I took points off if you did. What were you supposed to have referenced in Lab 3? You're looking for shapes of distribution, and I cited 2 other shapes that we often find. Okay, well, bimodality is what we found for the population of birth rates, but in the intro I talked about a uniform distribution and a... Okay, just a comment. For the test, on the short answers, it includes material in the labs, as well as the text, as well as lectures. Exponential. Exponential and uniform were discussed as part of that lab. Now, a uniform distribution is also referred to as a rectangular distribution. And in this problem, number 2, that you're asking about, we have a distribution that is rectangular. More to the point, I believe it's a square. Agreed? Now, see if I can make that look like a square. Something of that nature. Now, what was one of the requirements of a density curve? I divided by the square root of 2 pi in the density curve or the equation for the density curve for the bell-shaped curve. Remember, we had e to the minus x squared over 2 all over the square root of 2 pi as long as mu was 0 and sigma was 1. That was called the standard normal curve. Why did we divide by the square root of 2 pi? Okay, that I had hoped would resonate with you a little bit better. The area under the curve must be what?
Equal to 1.
Equal to 1. Thank you. Now, that's difficult to justify here because you would have to be able to do the antiderivative, what we call the definite integral. Here, it's pretty easy. This was to have a height of 1, I believe. And it was to go from 0 to 1, correct? And so the area of a square is the side squared, which is 1, so the area is 1. So it is a density curve. It is at or below, I should say at or above, not below. It is at or above the x-axis, which is another requirement of a density curve. Okay, which is one of your short answer questions. What are the properties of a density curve for a continuous random variable? And it is that the area under the density curve must be 1, and furthermore, that values of y must be greater than or equal to 0. Now, one of the things that we are interested in doing is related to the empirical rule. So just a reminder, we had the empirical rule. We talked about the change in curvature for this and where it would occur. And so we argued that we wanted in a bell-shaped curve that if you stayed within the plus or minus 1 standard deviation, you'd have what? 68% of your data. Now the argument is, much like we did in Lab 2, that the relative frequency, this 68%, is the probability of getting a value in that interval. We said 25% of your countries were in Africa, therefore draw a country at random. The probability is that 25%. So the probability of getting a number between plus or minus 1 standard deviation of the mean for a bell-shaped curve is 68%, or 0.68. Well, within that idea, you're supposed to answer questions about this uniform distribution for a continuous random variable x between 0 and 1. So some of the values that you were asked to address in number 2, what percent of the observations are between 0.25, so if this is the middle and this is 0.25 and this is 0.75, 1/4 and 3/4, then the answer to that is the area underneath the density curve between what? Those two values. So what is the area of this rectangle between 1/4 and 3/4? It's a half. So the probability of getting a value of x between 1/4 and 3/4 is the area underneath that density curve. So it is 1 times 3/4 minus 1/4, which is 1 times 1/2, which is 1/2. Now that's belaboring the issue to a degree, because that's pretty obvious just looking at the rectangle you create. But those two problems are related. This is a rectangular distribution. And that's the kind of documentation I expect for your answers. Draw the picture, show the area, and relate it to a statement about probability. The rest of the problem you should be able to do now. Any further discussion on that? Okay, let me just comment. I could have a triangular distribution. In which, I don't know if I've drawn this to scale, but let's say this is 0 to 1 and this is 2. And I argue that that's my density curve. Is the area underneath the density curve equal to 1? Give me an argument.
Because the area of the triangle is 2 times the length times the width divided by 1/2. Right.
Okay, you're talking about length and width, and I don't have a rectangle, so I'd like you to improve your reference. How about base and height?
Sure.
Okay. H for height, B for base, but you have 1/2 the base times the height, not twice. So your area for the triangle is 1/2 the base times the height. In a pre-algebra course, we would allow you to write B times H over 2, where you use the X for multiplication. In algebra, you would no longer use the X. You would just say BH over 2. Okay, so the base is 1, agreed. The height is 2, so I'm going to have 2 times 1 over 2, and so that area would just be 1, agreed? So I have a density curve. Now I could ask you for the area between 1/4 and 3/4. Same question. So this is again my halfway point, about right there. So there's 1/4, there's 3/4. So let me indicate to you the diagram I now have. And how are you going to find this area Any suggestions? And answering this question, and by the way, it's a good test question, is related to what we did with the table A, finding the area under a bell-shaped curve. What would you suggest? Since I suspect most of you have a background in geometry that would be limited enough, you probably want to look at this in terms of triangles. So how would you approach it?
Use the z-scores?
No, I wouldn't use z because it's not a bell-shaped curve. I can't use the z-score for either the uniform or the triangular distribution because they are not bells. Yes?
You would calculate the area of the small triangle, because they're all like, and then you would calculate the area of the shaded.
Okay. So what's being suggested is I have a larger triangle that is going from 1/4 to 1. Okay, that's this triangle that includes not only the shaded part, but this little portion right here. Okay, so the question, what is the base here? 3/4, agreed? Now what is not so clear is how you're going to find the height of that triangle.
What's the ratio between 2 to 1? So that
Well, we could use what we call similar triangles, or you could get the equation of the density curve and plug in x for that, and then get y that way, which is the way I would prefer algebraically to approach it. But before we go there, then we have a little triangle that we're going to find the area of, that we're going to then subtract that area from the big one, and this one goes from what? 3/4 to 1, but again, that allows me easily to get the base, but not get the height. So my question, what is the equation, and this is anticipating chapters 4 and 5, what is the equation of the line I drew for the density curve right here?
5 plus minus 2x plus 1.
Ah.
But plus 2.
Okay, we know that slope-intercept, I'll agree with Sean in the sense that it is a plus 2 because you're intersecting where? The y-intercept is 2. So we know it's going to be a 2 here. Now you have to be cautious as to how you get the slope of that line. So in a sense, as I go from 0 to 1 on this line, I go from a y value of 2 to 0. So the change in y is negative 2 over the change in x, which is 1, which is your definition of slope. And so I have minus 2x plus 2. So I'll concur with your modified answer. Now, if that doesn't ring a bell, and I remind you that m is y sub 2 minus y sub 1 over x sub 2 minus x sub 1 from Math 70. So I'm not discussing anything out of intermediate algebra. This is back to basic intro for algebra. Then once I have this equation, how do I find y when x is 1/4? Well, I would say y is equal to negative 2 times 1/4 plus 2. Okay, so that's minus 1/2 plus 2, which is 1.5, which is 3/2. So this ordered pair up here is at 1/4, 3/2. So the height of this now is going to be 3/2 times the base, which is 3/4, divided by what? 1/2 base times height, divided by 2. So that's 9 over 8 divided by 2, which is 9 over 8 divided by 2 is 9 divided by 8 all over 2. Invert and multiply. How about 9/16? Okay, now that was pre-algebra, our Achilles heel. What about this one now? How am I going to find that one for its height? Play the same game. Y is equal to negative 2 times 3/4 plus 2. So y is equal to what? That's minus 3/2 plus 4/2, which is minus 3/2 plus 4/2. 1/2. So that's pre-algebra. Okay, we are regressing back to counting. Okay, so this is going to be then 1/2. Okay. So my area now is going to be the 1/2 times the 1/4 divided by 1/2, and so that's what? 1/8 divided by, I'll hold it just a minute. I screwed that one up. I should have said divided by 2. I inverted and multiplied simultaneously. I was blowing that badly. 1/8 divided by 2, which is 1/16. So this area is 1/16. So what is the area I want? And if I'm in your way, look at the cameras, the television monitors. So what is the area you want now? 1/2. 9/16 minus 1/16 is 8/16, which is 1/2. That is a decent question on a test. No z-scores, just find a little bit of area, and it's a little more interesting than the problem that was asked. It also blatantly suggests that our algebra skills might need being reviewed, and that our arithmetic skills are what? Not quite up to the calculations involved in this problem. Okay, we'll leave it at that. That is a very extended solution to problem 2 covering new material. And as I say, that question about the triangle is and has been in the past on a test in the first exam. Okay? Not guaranteeing it'll be in this one, but it's been in past exams. Okay, that was one of 5 questions asked. So let's go back to center and let's see what else we can do. It's very clear that I'm not probably going to get much beyond these questions if I take as long as I did in this one. So I need number 12. Oh, 12 we don't. Okay, well that's good. But you're trading it off for a different one? Well, I'm not sure we can trade off. I mean, what do we get if we make the trade? You know, if the football season on, we make trades, we should get at least a draft choice for the next year or something to make it worth our while to consider doing that.
Get a better grade.
Oh, better grades. Okay, that seems reasonable. Okay, page 83. This is referring to table A, which is your Z table. I always find that interesting. The last letter of the alphabet for Z, you go to the first letter of alphabet for the table, table A. I believe it's on page 684. Is that right? 684 and 685 if we need to reference it. This is the problem that we tried to illustrate with several questions I asked you on Thursday. I said if you had 5% of your area to the right of your Z value, what Z would you get? And your answer to me was 1.645. I ask you, if you had 10% to the right of the Z value, what answer would you get for your Z value? And you answered 1.28. We called those values critical values. So in this sense, if I look at 13b, I want 40% falling above my value. And this is not typically of interest to me. But if I want 40% above, I have 2 ways of approaching it. I can use symmetry and find the negative value of Z that gives me 40% below. Or I can find on page 685 the positive value of Z that has 60% below. So it appears, yes, I'm going to have to migrate. So at this point, let me go to 684, put that underneath the document cam, and then I need to draw a diagram that makes it a little bit easier to explain the problem. This is a rather crucial problem that we're dealing with here. But let me bring the document cam down to a number that is close to where I'd like to be. The camera is drifting downward right now. It's about touching the page. So let me see if I can crank it up a little bit. There, we got some stoppage. Now, as I look at those numbers, I'm at the bottom of the page in 684. I'd like you to note that as I point at this page now, and I think we can see that somewhat, the numbers I need to look at are right here. I see a 0.4013. Hold on, I wanted 60%, 40% to the left. Okay. So I'm looking at 40% on the left side of the curve, and I'm right between these 2 numbers. So I'm 3 rows up from the bottom, and I appear to be between a what? A 05 and 06 column. So if I ran across to the side, it looks like I'm about negative 0.25. So let's leave that there. And I'm going to go over to the other side. I'm going to draw a curve again, a bell-shaped curve. Again, a reminder, you should be drawing bells. Okay? Now, as I come to this, I'm interested in a value somewhere over here that has 40% of the area to the right, correct? Now, that is symmetric to a value on this side. Now, I'm going to get the line of symmetry just by coming across. There is associated over here also a what? A 40%. Now, this value will be positive, this value will be negative. And I'm suggesting to you that if you use a Z of about negative 0.25, you have 40% to the left of that value. So the value you want to have 40% to the right is what? Not negative 0.25, but a positive 0.25. So I would expect to diagram something like this and to say the probability that z is greater than or equal to 0.25 is approximately 40%. Got it? Now, I'm not asking you to interpolate. Which is it closer to, 2.5 or 2.6? Back to the table, if you would, please, Jennifer. Let's see, I'm seeing a 0.3974, which is off by 26 ten-thousandths, versus a 0.4013, which is off by 13 ten-thousandths, so I'm closer to what? The 0.25. Any discussion as we come off there? Okay. Let's go back to the document cam for just a moment. It gives me some time to get back to center, and we'll look at another problem. Remember, we are concerned enough about the 5%, the 10%, and 1% values that we memorize those and call those critical values. So 2.5%, for example, to the right of your value is when z is 1.96. So the values we had were z at plus or minus 1.645, plus or minus 1.96, plus or minus 1.28. Those were values from Thursday, and those should be values you remember in your head, not just in notes. Okay, that was number 13. Moving right on now to number 31, inverting the digits. So I'm going to go to chapter 331. And in this problem, standard normal drill. Well, it's the same problem in the sense that you have in a standard normal distribution, you want 0.8 to be less than that, which is 20% to the right. It's the same problem, so I don't see a need to cover that. Part B, find the number z such that 35% of all the observations are greater than z. Okay, so that's 35% to the right. Take your 35 on the left. It's the same problem. So what we did in number 13 is the same way you approach number 31, so let's go on. That brings us to number 42. Okay, in number 42, this is talking about the quartiles, first quartile and third quartile. So this is simply relating it back to what we were doing. And in doing it, let's see, if we want to, what are the quartiles of the distribution ACT scores? And that is referenced way back between 31 and 32. So in the ACT score, let's see what we have here. The distribution, normal with a mean of 20.9 and standard deviation of 4.8. So let me try to bring that up on the camera. Here's the ACT scores as we go to the document cam. Not as readable perhaps as I'd like, but let's take the statement that those scores are approximately normally distributed. So this is X is normally distributed, and I need to come back just for a moment so I can read that. Let's see, I just lost it. ACT, is that the 20 point and 4.8? So I have a 4.8 for the standard deviation, and what was the 20.5? 9? 20.9. So that's my information. We can now come to the board. Normal distribution. Now I'm asked to find, in essence, the first and third quartile. Now if I have raw data, we know that we have to rank the data, we have to find the median, then we play halvesies. We've illustrated that. But here's a case where I'm interested in looking at this bell-shaped curve again, and I'm interested in getting a value, let's see. Now, we know something about where to locate these two numbers. Because as I look at this, these are where the curvature change. So what do I have to the left of where the curvature is changing? And why? Give me a number. Hint, empirical rule. What is the area under the curve between plus or minus 1 standard deviation empirical rule? 68%, correct? So what does that leave for the tails? Combined, 32. Half of 32? 2 into 32. 16. I now understand why your answers sometimes are delayed. You have not remembered how to think without a calculator with numerical values. Okay, so if this is 16%, do I want to be to the right or to the left to get 25%? I heard somebody say left, I heard somebody say right. If I go further to the left, I'll have less. Go to the right, I'll have more. Huh? So I don't know how much more, but let's just, at least we know we have to be to the right of that curvature. So I want 25% of my data in that region. Okay, now you need to find me the z-value that will do that. So you're going to go back to the table, 684, 25% on the left. I need a z that'll do it. Does somebody have that z? .67, am I hearing? .6, negative .675? So you were able to interpolate and play halvesies. Agreed? Now what can I do to find the x that I'm interested in? We now use a basic solution from elementary algebra, and I would even do this in pre-algebra. I'd even do this in a Math 10 nearly. You write the formula. You substitute what you know. This is negative .675. I'm hunting for that x. Do I know mu? It is 20.9. And put that over 4.8. And then realize that I have an equation. Drop that just of a smidge. Thank you. And cross multiply and solve for x. Enough on that one. Okay, so that was number, what, 42? And that's how we could find quartiles if we have a normal distribution. So that's the solution. And boy, that doesn't look all that clear up here. Interesting. Not sure why. The focus on the screen doesn't look as much, with much clarity as I'd like. Number 46. And we may make it yet. Okay, 46. A surprising calculation. I'd say this morning I'm surprised at many of them. A surprising calculation. Changing the mean of a normal distribution by a moderate amount can greatly change the percent of observations in the tails. So we look at, suppose that a college is looking for applicants with SAT math scores at 750 or above. Okay, and this is one of the criteria that a college or university might use to recruit students. So we have, in 2004, the scores of men on the math SAT. You're told that they were normally distributed with 537 and 116, meaning the mean is 517, standard deviation of 116. The women were at 501 with a 110 standard deviation. Obvious question. Why are the scores for men more than women? And if you've been around academia very long, this is a very dicey question to argue. It cost a university presidency for somebody who argued one way. The gap seems to be closing in this, by the way. But nonetheless, the key here is that the standard deviation being smaller could make the same difference between x and mu end up with a different z. Let me come to the sideboard and reflect here on something that we started the hour on. we looked at this. We argued this was 11. This was the square root of 30. And we said roughly 3.6 or 7. So I'm going to use roughly 3 2/3 at 3.7. Now, if I look at a z-score, this is related to the problem, but it's related to what we've done earlier. If I looked at a particular birth rate, okay, and by the way, the mean of those birth rates was at about 22, was it not? About 22. So if I look at this, and if we had a normal distribution, and by the way, this is very flawed because you learned from Lab 3 that we don't have a normal distribution of birth rates. So this calculation is not going to be as accurate as I'd like. But if they're centered at 22, and I were to take something at about 44, which is getting up near Niger's rate, correct? We're getting up into that very high region. And I divide by 11, this is going to give me about 2. And the area to the right of 2 is roughly 2%. 2.5%. Empirical rule, the mean plus or minus 2 standard deviations, 95%, 5 in the tails, half that's 2.5%. So I could argue here that the probability that z is greater than or equal to 2 is about 2.5%, or that's 0.025. Okay. Now, if I look at this same question for an average, so again, what I'm doing is giving you a formula that we haven't talked about, but it comes out of what we talked about at the beginning of the hour. My point being, this standard deviation down here is now 3.7. The same values up here. Okay. But now this is 11 over what? This 3.7 roughly, or I should say 22 over the 3.7. How big is that? Now you can use your calculator. 22 over 3.7. I was going to ask you to estimate that. I have learned something. Don't ask that question. Okay, what do you have? (22 over 3.7) equals on your calculator. What do you get? Roughly 6. Yes? Now, what's the area to the right of 6? Very, very small. Okay? Look at your table, 685. Go to 685 for a moment. I think your table only goes up to about 3.5. 685. Good idea. Copy the table and put it in your notes so you can reference. I like that. 685. Are you seeing a 3.5 at about the highest you can go for z? And as you go to the very far end, that's going to be about 0.999 something for the area to the left. So what does that leave for the area to the right? Just at 3.5. Okay, I'm going back to the center. We're getting looks of confusion on many faces, so let me go back to the table and try to reference what I'm talking about. 685, and I ask you to go at the very bottom of the page, bottom right corner, you find a 0.9998. That's at 3.49 for z, correct? So that says the area to the left of 3.49 for z is 0.9998. So what's the area to the right? 0.0002. Now if I go further down, what do you think is going to happen? I'm going to get a smaller and smaller number to the right. So my guess is to about 6 digits, you're going to have 0. Compare that, going back to the sideboard, of 2.5%. So what's changed in this problem? Otherwise, this comes out for the area to the right of a 6 is less than 0.0002. That much I know. This was at 0.025. This is less than 0.00. I don't have enough zeros. 0.02. Sorry about that. Much smaller, right? And the only thing that has changed is the standard deviation. Okay? So small changes in x values could mean huge changes in z if the standard deviation is what? Very small. Otherwise, to say that a change of 2 points for x might result in a huge change in z is going to depend on how big your standard deviation is. So if I end up with a z-score of 2 in the numerator and 2 in the denominator, I'm just going to get a 1, and that means about 16% to the right. But if I have a 2 here, and this is a point, say, 0.25, or let's just say 0.5, then this is going to go 4 times, and now the area to the right of 4 is less than 0.0002. Same change, but the standard deviation is determining what? The z value, and the z value gives me the area under the curve because I'm ultimately typically asking, what's the probability that z is greater than or equal to 1? Answer, 16%. What's the probability that z is greater than or equal to 4? Less than 0.0002. What was the only thing that changed? Standard deviation. That's what really is being talked about in problem 46. I'm going to ask that your homework get turned in today. I don't have the luxury of continuing with it. We've got to get into Chapter 4 and Chapter 5. Bring your calculators tomorrow. I need to have you review how to find the equation of a line from 2 points, review slope, review plotting, slope-intercept form for the equation of a line. Lots of algebra you need to review. It's in the student study guide if you don't have an algebra book. So as we go back to Fleetwood Mac, and what's your choice as we close down, Jennifer?
Go your own way.
Well, go your own way, but do it